Welcome to the deep dive. Ever wonder how Netflix recommends your next binge watch? Or how Google surfaces the exact web page you're looking for out of, well, billions?
Yeah, it's pretty amazing when you think about it.
It all boils down to finding things that are similar really fast, even when you have just a mind-boggling amount of stuff to search through.
Hmm.
Today, we're cracking open the hood on some new technology that's making waves in this area. It's hinting at a future where searching truly massive data sets becomes surprisingly accessible.
That's right. Think of all the digital information out there, images, songs, articles, you name it. To a computer, these can often be represented as lists of numbers, what we call vectors.
Vectors, right?
And these vectors, they sort of live in this high-dimensional space. The closer these numerical lists are to each other, the more similar the actual items are.
Okay.
So when you search for something, you're essentially asking the computer, find the closest vectors to my query vector.
Okay, let's unpack this maybe with a simpler example. Like, imagine you're trying to find a specific shade of blue paint in a huge catalog.
Sure.
Each shade could be described by numbers representing its brightness, saturation, hue. That's our vector, right?
That's the vector.
The closer the numbers, the more similar the shades look. Now, if you have millions of paint swatches, how do you quickly find the closest matches to the blue you have in mind without comparing it to every single one? That sounds slow.
Exactly. And that's the core problem. With billions of data points and these vectors having maybe hundreds or even thousands of dimensions, that straightforward approach of comparing your query to every single item, it becomes incredibly slow.
Yeah, I bet.
It's like trying to find one specific grain of sand on an entire beach. That's the essence of the cursive dimensionality.
Right.
This is why we need clever shortcuts.
Yeah.
Ways to find approximate nearest neighbors, things that are really close, really fast.
So it's not about finding the absolute perfect match every single time, necessarily.
Not always, no.
It's about something darn close and getting it back to us in, like, a blink. How do we even measure how well these close enough methods are actually doing?
Well, a common yardstick is something called k-recall at k.
K-recall at K, okay.
Let's say you're looking for the single most similar item, so k equals 1. The algorithm gives you one result. The one recall at 1 tells you how often that one result is actually the true, absolute closest item.
Okay.
Or if you're looking for the top 10 most similar, so k equals 10, and the algorithm gives you 10 results, the k-recall at k tells you what fraction of those 10 results are actually within the true top 10.
Got it. So it's a measure of accuracy, pretty much. And there are already ways to do this approximate search, right? This isn't a totally new problem.
Oh, absolutely not. Researchers have developed various techniques over the years. Some, like KT trees, work well in simpler cases, but they tend to stumble as the data gets more complex, more dimensions.
Right.
Another approach, locality-sensitive hashing, or LSH, tries to group similar data points together, sort of like hashing them into buckets, so you only need to search within likely buckets.
Hmm.
And then we have graph-based methods like HNSW and NSG, which are quite popular now. They build these interconnected networks of your data points, letting you navigate quickly to similar items.
And they all have different trade-offs. Speed, accuracy, memory use.
Exactly. Strengths and weaknesses for each one.
And this is where our deep dive takes a really interesting turn. Because our listener today wants to understand how we can tackle truly massive data sets. We're talking billions of data points efficiently.
Yeah, the billion scale challenge.
And the long-standing belief, this sort of conventional wisdom, has been that this requires enormous amounts of main memory, RAM, the kind you find in really powerful servers. But today, we're diving into a new kid on the block called DiskANN. And it kind of throws a curveball by suggesting, hey, maybe we can do this on a single machine with, like, a relatively modest amount of RAM and something most modern computers have.
An SSD, a
Oh.
solid-state drive. And what's really exciting, I think, is that DiskANN challenges that core assumption that searching on an SSD is just inherently much slower than searching in RAM.
Which everyone sort of assumed, yeah.
Pretty much, yeah.
Yeah.
But the research we're looking at shows DiskANN can not only keep pace with in-memory methods for these huge data sets, but in some cases, actually outperform them on a single machine.
Wow.
Imagine being able to search through a data set the size of, I don't know, all publicly available research papers, maybe. Not on some giant server farm, but on a powerful workstation sitting under your desk.
That really changes things. So our mission today is to unpack DiskANN and the engine driving it, this technology called Vimana.
Vimana, right.
We want to understand how it enables this seemingly impossible feat fast, accurate, billion-point nearest neighbor search on a single machine with limited RAM and just an SSD.
Let's do it.
So let's start by looking at why this has been such a big challenge. What were the main ways people tried to tackle this scale before DiskANN, and what were their limitations?
Okay, so the research paper we're digging into highlights two main strategies that were common for handling these really colossal data sets.
Right.
The first involves using something called an inverted index, combined with compressing the data quite heavily. Think of tools like AIs, specifically methods like IVFOADC plus G plus P.
IVFOADC. Wow, okay. Catchy name.
Yeah. The basic idea is to organize the data into manageable chunks, like an index in a book, and then squish down the size of each data point's vector using compression.
To make it fit in memory.
Exactly. So the entire index can fit into RAM.
Okay, so the big win there is definitely keeping the memory footprint small. You could have an index for billions of items living in, say, 64 gigs of RAM.
Right. And with specialized hardware, like GPUs, the search itself could be pretty quick, too.
But there's got to be a trade-off. You mentioned compression.
There is. That compression is lossy. It means you're sacrificing some of the original detail in the vectors to save space. And the paper points out that because of this, these methods might only achieve around, say, a 50% chance of finding the absolute closest match when you're just looking for that one top neighbor. So 50% one recall at 1.
Only 50%. That doesn't sound great for some applications.
It might not be, yeah.
Yeah.
They can get much better results if you look at, like, the top 100 results returned. But often, you really need that number one result to be accurate.
Right, so it's a balancing act. Memory versus precision.
Precisely.
Okay, what was the second major approach?
That involves taking your giant data set and basically chopping it up into smaller, separate pieces or shards.
Sharding, okay. Heard of that.
Then you build a standard in-memory search index for each of these smaller shards. The paper mentions, for example, Taobao, the e-commerce platform. They apparently divide their 2 billion items across 32 different machines.
32 machines.
Yeah. So when you search, your query gets sent out to all 32 machines simultaneously. They each find the best matches within their own little piece, and then those results get gathered up and combined.
Okay, so this way you avoid that lossy compression, which probably means better accuracy.
Generally, yes.
Better recall.
But the downsides seem pretty obvious. You need way more memory overall, spread across all those machines.
A lot more memory, yeah. And more hardware.
Plus, coordinating queries across 32 machines must add time, latency.
Definitely adds latency.
Yeah.
And complexity. And the crucial point the paper makes is that both of these dominant strategies, compression or sharding, ultimately hit a wall because they rely so heavily on having enough main memory, enough RAM.
Right.
The prevailing wisdom, even stated by the folks who developed Phase, was that moving these kinds of search structures onto a disk, even a fast SSD, would just make searches way too slow.
Because of the disk access time.
Exactly. The latency of those random disk reads, even if it's just milliseconds. The thinking was that they'd add up and absolutely kill performance for this kind of interactive search.
Okay, so DiskANN comes along and basically says, hold my beer. How do they challenge this? What's their fresh angle? Well, DiskANN is presented as an approximate nearest neighbor search system, specifically designed from the ground up to live on an SSD. And the core of their innovation is this new graph building algorithm called Vamana. Okay, and the headline result is really quite startling. They claim they can index and search through 1 billion data points with very high accuracy. We're talking over 95% one recall at 1.
95% on 1 billion points.
Wow. And do it with really low latency, less than 5 milliseconds on average, all on a single workstation with just 64 gigabytes of RAM and an SSD. Okay, that is a game changer if it holds up. So Vamana is the secret sauce here. Let's dig into how it works. We know it's a graph-based approach. What's the general idea behind using graphs for this kind of search? So imagine you're trying to navigate a complex city, right? A graph in this context is like a map. Each location that's our data point, our vector, is a node, and the roads connecting them are edges, linking similar locations or points. The idea in graph-based ANNS is to build a well-connected map, a good graph. Then, when you have a query, you start at some point on the map, and you follow the roads, the edges, to progressively closer or more similar points until you find what you're looking for.
How do you follow the roads? Just randomly?
Usually using a greedy approach. At each step, you look at your current location's neighbors, and you move to the neighbor that seems closest to your target query. Keep doing that, hoping to zero in.
Makes sense. The paper mentions something called sparse neighborhood graphs, SNGs. Says they're ideal, but not really practical.
Yeah, SNGs are sort of the theoretical holy grail.
Mm.
Imagine a graph where for every single data point, its connections, its edges are so perfectly chosen
Huh.
that if you started a greedy search from anywhere in the graph, you'd quickly and efficiently reach any other point just by always moving to the neighbor closest to your target. Like a perfect road network with no wrong turns, always the most direct route.
Sounds amazing. Why can't we just build that?
Because figuring out those perfect connections for billions of points in high dimensions is incredibly computationally expensive, just prohibitive, not feasible in the real world.
Right. Okay, so Vimana is trying to build something like an SNG, but one that we can actually construct.
Exactly. It's trying to approximate that ideal structure.
Yeah.
And a key part of that is what they call the robust pruning procedure. Think of this as a really smart way of deciding which roads to build on our data map.
Robust pruning.
Oh,
Ever?
instead of just connecting each point to its absolute closest neighbors, this procedure uses a parameter, they call it alpha, to guide the process. It helps ensure that the connections we create are actually useful for making rapid progress during a search.
So it's not just about being close, but being strategically connected for faster travel.
Precisely. It's making sure that when you follow an edge, you're not just moving slightly closer, but making significant headway towards where you want to go. Alpha helps control that.
Interesting. Okay, so how does the overall Vimana indexing algorithm, I think it's algorithm 3 in the paper, use this robust pruning to build the actual search index?
Right. So the Vimana indexing process builds the graph step by step. First, it initializes things with a basic, randomly connected graph, just gives every point a fixed number of random outgoing connections.
Just to get things started.
Yeah, ensures everything's connected somehow, even if poorly. Then it picks a central point, a medoid, which acts as a good universal entry point for searches later on.
Okay.
After that, it iterates through all the data points, usually in a random order. For each point, it performs a kind of exploratory search on the current state of the graph. Like, if I started near here, where would I end up visiting?
Uh-huh.
It collects this set of visited points. Then it applies that robust prune procedure to this set to decide which of these visited points should become its actual outgoing neighbors
Yeah.
in the final graph using that alpha parameter.
Pruning down the possibilities.
Exactly. And importantly, it also adds backward edges. So if point A connects to point B, it makes sure B also points back to A. This reinforces good pathways. If adding edges violates the maximum degree limit for a node, it uses robust prune again to remove less useful edges.
And this pruning is crucial for keeping the graph efficient, right? You don't want it getting too dense.
Absolutely. Robust prune, algorithm 2, is like the quality control editor. Given a point and a bunch of potential neighbors it visited, it uses alpha to select the ones that offer the best combination of closeness and navigational progress. It keeps the graph relatively sparse but effective.
The paper also mentions doing this whole indexing thing in 2 passes. Why go through all the data twice?
Yeah, they found that a 2-pass approach actually yields a better quality graph in the end and can paradoxically be faster overall.
Faster.
So the first pass uses a specific alpha value, alpha equals 1. This focuses on building a solid baseline connectivity, ensuring the graph is well connected everywhere. The second pass then uses the user's desired alpha, which is typically greater than 1. This pass refines the connections, adding maybe longer-range shortcuts that help speed up the search even more.
And why is that faster than just using the final alpha from the start?
They observed that if you start with a high alpha right away, the graph can become too dense too early, making the greedy searches and pruning steps within the indexing process itself much slower. So 2 passes turns out to be more efficient for construction.
Clever. Okay, so Vimana has this tunable alpha for pruning and this 2-pass build. How does it stack up against the other graph methods we mentioned, like HNSW and NSG? Are they similar?
There are definitely similarities at a high level. They all iterate over the data, use some form of greedy search to find candidate neighbors, and then apply some pruning logic to select the final connections. But the key difference is Vimana's explicit tunable parameter. HNSW and NSG effectively operate as if alpha is fixed at 1. This tunability gives Vimana potentially more control over that critical trade-off between the graph's density, how many neighbors each point has, and its diameter, how quickly you can get across it.
So a higher alpha in Vimana is like saying, I want fewer connections per point, but make damn sure they're really good ones that help me jump further across the graph.
That's a good way to put it, yeah. Another difference is which nodes they consider for pruning. Both Vimana and NSG look at all the nodes visited during that exploratory greedy search phase when deciding on connections. This can lead to incorporating longer-range links more naturally.
And HNSW.
HNSW primarily focuses its pruning on the final set of nearest neighbors found by the greedy search. This tends to create more local connections. To get the long-range connectivity, HNSW relies on its distinctive multi-layered hierarchical graph structure.
Ah, the layers in HNSW,
Yeah.
right.
Brahman also has a simpler initialization, just starts with that random graph, whereas NSG often starts by building a more complex, approximate k-nearest neighbor graph first, which takes time.
Okay.
And as we just discussed, Vimana uses those two construction passes, while HNSW and NSG typically build their index in a single pass.
All right, so Vimana seems pretty smart about building these search-friendly graphs, but we still haven't quite closed the loop on the huge challenge. Billions of points, limited RAM. How does DiskANN, the system, actually manage this using Vimana on an SSD?
Right. This is where the system design really shines for these massive scales. DiskANN uses a clever strategy they call overlapping partitioning.
Overlapping partitioning.
First, it takes the billion data points
Mhm.
and uses a standard clustering method, like k-means, to divide them into a manageable number of initial groups, maybe 40 or so.
Like breaking the problem down.
Exactly.
Yeah.
But here's the key twist. Instead of assigning each data point to only one group, it assigns each point to the, say, closest group centers, usually as small, like 2.
So a data point can belong to 2 different initial groups. Why?
That overlap is crucial. Because now, for each of these smaller overlapping groups, DiskANN builds a Vimana index completely in main memory. Since each group is maybe only, say, 50 million points instead of a billion, this fits within that 64 GB RAM limit.
I see. You build lots of smaller Vimana graphs in RAM.
Precisely. Once you have these, say, 40 individual Vimana graphs, DiskANN merges them into one single large graph. It does this simply by taking the union of all the edges from all the smaller graphs.
Just combines all the connections.
Yep. And because those initial clusters overlapped, there's enough connectivity built in to ensure that the final merged graph works well, even if a query's true nearest neighbors were initially split between different groups. The overlap provides the bridging connections.
That is a really neat way to build the index without needing terabytes of RAM. Okay, indexing handled. What about the actual search? You still have a billion full precision vectors somewhere. How do you avoid hitting the SSD constantly?
Good question. This is where vector compression comes back in, but in a different way than the IVF methods. DiskANN creates a smaller, compressed version of every single vector using something called product quantization. PQ. Product quantization, okay. These PQ codes are much smaller than the full vectors, small enough that DiskANN can keep the compressed codes for all billion data points resident in the fast main memory, RAM.
All billion compressed codes in RAM.
Yes. So during the initial stages of the search, when Vimana is navigating the graph, it uses these fast-to-compare approximate PQ codes in RAM to figure out which neighbors look most promising, guiding the search path.
So the graph traversal logic, the which way to go decision, happens quickly in RAM using approximate distances. But eventually, you need the real deal for accuracy, right? The full vectors.
Absolutely. You need the full precision to get that 95% plus recall. So the Vimana graph structure itself, which is essentially just lists of neighbor IDs for each point, and the actual full precision floating point vectors for all billion points are stored together on the SSD.
Okay, graph and full vectors on the SSD. How are they laid out? Is it just random?
No, the layout is critical for performance. For each data point ID, they store its full precision vector, and then immediately following it on the disk, they store the list of IDs of its neighbors in the Vimana graph.
Vector followed by neighbors.
Yes. And they pad the neighbor list if necessary, so every point's record takes up the exact same amount of space on disk. This makes it super fast to calculate the exact disk offset for any point's data just from its ID. No complex lookups needed.
That structured layout sounds key to minimizing those slow random disk seeks. How does the search process actually use this layout on the SSD?
DiskANN employs a technique called beam search, specifically optimized for SSDs. Instead of just fetching the neighbors for the single most promising candidate at each step of the graph traversal.
Like standard greedy search.
Right. Instead, it maintains a small set or beam of the current best candidate points, say the top W candidates. W might be 4 or 8 or maybe more. In one go, it fetches the neighbor list for all W points in the beam from the SSD.
Why fetch all W at once?
Because reading a slightly larger sequential chunk from an SSD is often almost as fast as reading a tiny random piece. By fetching neighbors for W points together, it dramatically reduces the number of separate, slow round trips to the SSD compared to fetching them one by one.
Fewer, bigger reads are better than many small reads on SSDs.
Got it.
Yeah.
Is there a limit? Can W be huge? There's a trade-off. A larger beam with W means fewer SSD round trips, but it also means more computation, more distances to calculate, and potentially hitting SSD bandwidth limits if you try to read too much at once. So you tune W.
Okay, beam search minimizes SSD trips for neighbor lists. What about very popular nodes in the graph, things that get visited all the time?
Good point. To speed things up even more, DiskANN allows for caching. You can keep the graph information, the neighbor lists, for frequently visited vertices in RAM.
How do you know which ones are frequent?
It could be based on past query patterns, or, more simply, they suggest caching all nodes within a certain small radius, say C hops, maybe C304, from the universal starting point, the medoid. Since most searches start there, these nodes get hit often. Catching them avoids initial SSD reads.
Smart. Okay, so we have the graph on SSD, PQ codes in RAM for navigation guidance, beam search minimizing SSD reads for neighbors, and caching for hotspots. How does DiskANN nail that high accuracy, that 95% recall, given it's using approximate PQ codes for navigation?
This is perhaps the most elegant part, what they call implicit re-ranking. Remember how the full precision vector is stored right next to the neighbor list on the SSD?
Yeah, vector than neighbors.
Because of that layout and the way SSDs read data in sectors or pages, when the beam search issues a read request to get the neighbor list for a candidate point, the SSD already reads the full precision vector for that point as part of the same I/O operation, essentially for free.
Oh, so you get the full vector data alongside the neighbors without an extra disk read?
Exactly. DiskANN keeps these fetched full precision vectors in RAM for all the points it visits during the beam search. Once the beam search decides it has explored enough, it takes all the candidate points it has encountered, looks up their full precision vectors, which were already in RAM, and calculates the exact distances between the query and these candidates.
Ah.
It then re-ranks the candidates based on these precise full precision distances to find the true top K nearest neighbors. This completely overcomes the accuracy loss from using the PQ codes during the graph traversal part.
That's incredibly clever. Use approximate for speed in navigation, but leverage the disk reads you're already doing to get the full data needed for final accuracy.
Precisely. And they contrast this with another method called zoom, which apparently does its re-ranking by fetching all the candidate full vectors in a separate step at the end, potentially causing a storm of random disk reads. DiskANN avoids that.
Very neat. So how does all this translate into actual performance numbers? The paper must have benchmarks.
Oh yeah, lots of them. First, they just evaluated Vimana itself as an in-memory index, comparing it against top contenders like HNSW and NSG on standard datasets like CIF-T1M, JAS-T1M. Vimana either matched or beat the others in terms of the recall versus speed trade-off. It was particularly strong on the JAS-T1M dataset. And importantly, Vimana often had faster index build times.
Faster building is always nice.
They also look specifically at the average number of hops or distance calculations needed to find the neighbors. Vimana, especially with a tuned alpha, generally required fewer hops to converge than HNSW or NSG. Figure 2C in the paper shows this. That's a good sign for SSDs, where each hop potentially means a disk access.
Few harps is definitely better for disk. Okay, what about the main event, the billion-point ANC 4MB dataset? How did DiskANN do there?
Right, the big one. They tested two DiskANN Vimana indices. One was the ideal index built using Vimana directly on a machine with massive RAM. They called this the one-shot Vimana index.
The unlimited budget version.
Sort of, yeah. The other was the merged Vimana index, the one built using their overlapping partition strategy entirely within the 64 GB RAM constraint of a normal workstation.
The practical one.
Exactly. Now, the one-shot index, as you'd expect, gave the absolute best performance. It actually set a new state-of-the-art for one recall at 1 on that dataset for single-node systems, achieving very high recall with latency around 2-3 milliseconds.
Impressive. But what about the merged one, the 64 GB version?
That's the really compelling result. The merged index, built within 64 GB, still significantly outperformed all other existing methods designed to run on a single node for billion-point search. As figure 2A shows, for a given recall level, like 95% one recall at 1, it was much faster than the competition. It was slightly slower than the one-shot index for the same recall, maybe taking 4 to 5 milliseconds instead of 2-3.
Why slightly slower?
They speculate the merging process might make the graph slightly less optimal, requiring a few extra hops during search compared to the perfectly built one-shot graph. But still, amazing performance from a 64 GB machine.
Absolutely incredible that they could build it and search it so well with relatively little RAM. How did it compare directly against those compression-based methods, like the IVFODC one?
The comparison is shown clearly in figures 2A and 2B. They compared DiskANN, both merged and one-shot, against IVFA-DC plus G plus P, which is often considered a very strong baseline, memory efficient and accurate for its class.
And the verdict?
DiskANN blew it out of the water, basically.
Yeah.
At similar low latencies, like under 10 meters, DiskANN achieved vastly higher recall, hitting over 95% one recall at 1, where IVFO-DC was struggling to get much past 50-60%, even with optimizations.
Wow, huge difference in accuracy.
Yeah. Even when comparing at similar memory footprints, DiskANN was way ahead on recall for the same speed. They attribute this directly to the lossy nature of the compression used in IVS methods. DiskANN builds the index using full precision and re-ranks with full precision, avoiding that fundamental information loss.
So DiskANN finds a way to get graph-based accuracy without needing graph-based memory requirements.
That's the key takeaway. They also briefly mention Zoom, noting its potential issues with random disk access during re-ranking and challenges in scaling its clustering approach.
Right. So let's try and sum this up. DiskANN, powered by this clever Vimana graph algorithm and smart SSD-aware system design, has basically shown that high-performance search through billions of data points isn't just for massive server farms anymore. It seems genuinely achievable on a single, pretty standard, affordable workstation with an SSD.
Yeah, it really shakes up the long-held beliefs in this field. It challenges the notion that you must have everything in RAM for fast, accurate search at scale.
It's like getting the best of both worlds, isn't it? The high recall and low latency we associate with good graph methods,
Right.
combined with the kind of memory efficiency and scalability that people used compression or sharding for. DiskANN found a way to blend them.
Exactly. It's a powerful combination, and it has huge practical implications for anyone dealing with massive data sets, researchers, companies, you name it.
It really does open up a world of possibilities. So, thinking ahead, with this kind of breakthrough, what exciting new applications or analyses do you think might become possible now that searching billion-scale data might be feasible on just one accessible machine?
That's the exciting question, isn't it?
And what are the next big hurdles, the next frontiers in pushing these boundaries even further? It really makes you wonder what other unbreakable rules in computing might be ready for a rethink.
Absolutely. That's exactly what you should be thinking about. This kind of democratization of high-performance search on massive data could unlock new discoveries. Think about personalized medicine, analyzing huge genomic data sets, or climate science modeling vast simulations, or even just better recommendation systems, fields where scale was the bottleneck.
Yeah.
As for the future, I expect we'll see even more innovation in hybrid approaches, cleverly managing data across SSD, RAM, maybe even newer persistent memory types, finding even smarter ways to navigate this ever-growing ocean of information without breaking the bank. The lines are blurring.
Fascinating stuff. Well, thanks for taking this deep dive with us today. Really eye-opening.
My pleasure. It's exciting work.
Until our next exploration.